So the next section of this lecture will be an introduction to statistical estimation. So what is statistical estimation? So we'll start with a quick recap. So this is you can view it as a just a recap of distributions and random variables, and actually not just about these things, but about the equivalence between these two quantities. I have highlighted it before, but I wanted to go over it a little bit again. And the next part will be about explicitly fitting distributions for data. Like I said, most of statistics is about actually guessing or in some sense viewing data as the output of a random process. Okay, and but it will be more than that. We will actually try to guess what kind of random process is generating the data, and we'll try to find its parameters. So that'll be the next thing, and the third thing that we'll look at is, once we phrase it as a question of finding the parameters, then we'll discuss how you can find the parameters given the data. Okay, and that's where this notion of an estimator comes up. An estimator is basically a statistic that lets you find probable values for these parameters. Okay, so we'll see what that means, and we'll also look at properties of estimators, what makes one estimator better than the other, and so on. Okay, so alright, so let's begin without further ado. So we have so the first thing I wanted to point out is this notion of equivalence between. So I keep saying that we assume data comes from a distribution, right? So what does that mean, right? So data is drawn from some distribution. Okay, and I will use multiple terms interchangeably, which is why I wanted to clarify them once and for all. Okay, so let's say you have some random process. Okay, so this is some random process, and this generates, let's say, a point for simplicity. So a point in the plane. Okay, so there are many equivalent ways of viewing this. So for every point in the plane, there is some probability that the random process generates this. Right? So for every x in the plane, I will write it as R2, because it's the real space of dimension 2. Okay, so for every x in R2, there is some probability, p of x. Okay, and if this is a continuous distribution, which is any point can be generated, then this will actually be this could be a probability density function. Okay, so now x is a two-dimensional vector over here. Okay, so to be very formal and stick with what we've done before, you'll have to have different PDFs for the first coordinate and different PDFs for the second coordinate. Okay, so for now let me not do that, and let me just write it as some p of x. Okay, now this, as I have defined it, is some probability density function, but we also typically talk about this random process as the point that is generated as a random variable. So also a random variable. Again, to be formal, you have to have two random variables. Let's call them capital X1 and capital X2. So these are the first coordinate, and this is the second coordinate. Or if you like, let's write them as x and y. And these, like we've seen before, these would be jointly distributed random variables. Okay, so this is an equivalent viewpoint of the whole picture. Okay, so whenever I talk about a random process producing data, you should be thinking about each data point as either being a random variable or it having some distribution. Currently, this is distributed like some random variable. Okay, so this is why we will. And if you remember, when we were discussing random variables, I kept highlighting this point that the distribution is all that matters. In some sense, you can think of a random variable and its distribution as basically equivalent definitions of the same thing. Okay, so this is one thing. This is the first point that I would like to mention, and this now hopefully makes it clear that at least what we had seen a few minutes ago in this IID assumption is basically like saying that this distribution that we have out here, this is what we write as D. Okay, and this is the output distribution of this random process. Okay, and now we imagine running this random process independently for n times. Okay, so our data points x1 through xn are all drawn from this D. Okay, and in this example, each of these would be like a two-dimensional point. Okay, so this is this just in case is it's a notational clarification in some sense. Okay, so let's now look at this second part, which is basically the main thing in statistical estimation. Right, so I said that the main idea in statistics is to assume that data comes from distribution, right? But is some distribution good enough, right? So most often in statistics, we go further than that. Okay, what we say is that data comes from a distribution of a very specific kind. Okay, so the most common assumption, for example, for real value data is this assumption that data comes from a normal distribution or a Gaussian distribution. Okay, so common for real value data is that D is actually a normal distribution of mean mu and variance sigma square. Note that this is something we had seen a few lectures ago. So this just means that the PDF for this distribution is centered around mu and it's symmetric, and it looks like this. Okay, so this is centered around this mu. Okay, and there's a complex formula for it which we also saw a few lectures ago. Okay, so and this is the most common distribution that people assume for real valued data, right? So you observe a bunch of points on the real line. So this is especially true when you make some physical measurements. Okay, so when you make some physical measurements, they will all be centered around some mean mu, and the way they drop off, so most of the points will be kind of close to mu, within roughly sigma of mu. You could be much further out, but the probability that you are much further out will be very small. Okay, and this is exactly what is captured by the normal distribution. Okay, so the probability that you are far out is small. Okay, so in fact, let me quantify this because it's something you should know. The probability that x is x minus mu, this is the distance to the mean. Okay, distance to mean is more than some constant c times sigma, okay, is so this one will be smaller than something like e to the minus c squared, okay, by 2 or something like that. Okay, so what this says is that the probability that you are, let's say, 5 sigma away, so let's say sigma is some quantity, and in this case let's say this length is sigma, okay, then the probability that you are like 5 sigma away, which means that you are above this point or maybe to the left of this point, is extremely tiny. Okay, so this is something like e to the minus 25 by 2, which is like e to the minus 12.5. If you compute it, this will be like a number which is like 1 divided by a billion or something like that. Okay, so that's the point that I'd like to make. So this Gaussian distribution, it has this property that as you go away from the mean, the probability really drops. Okay, and this sigma, which is square root of the variance, which is also called the standard deviation. So this gives you a quantitative way to measure this probability. Okay, so we will keep coming to this kind of a point later as well. Okay, so this is a very common model for real value data. Okay, so likewise, let's say I have binary data. So and this one, you assume if I have binary data, let's say I have a bunch of 0, 1, 1, 1, 0, 0 something. And so note that this is x1 is 0, x2 is 1, x3 is 1, and so on. This is what I mean by this data. And so here it's very common to assume we know only one source of binary data, which is coin toss. Okay, so it's very common to assume that this is a Bernoulli distribution with p being some parameter. Okay, so note that in doing these things, you assume that even in the previous case, you assume that d is it's some Gaussian with a mean mu and variance sigma, but you don't know what these mu and sigma are. Okay. Likewise here, if you have some binary data, you assume it's generated according to some Bernoulli distribution. Remember, Bernoulli is just a coin toss, and it's 1 with probability p and 0 with probability 1 minus p. Okay. So yeah, so this is what we assume. We assume it's Bernoulli with some parameter p, but you don't know what this p is. Okay, And the general so this question of estimation will essentially try to find this distribution P. Okay, so this is a common model that people use for binary data. Okay, and so now what is so the other thing that I would like to mention is sometimes you don't assume a structure for this distribution. Okay, so sometimes, so classical statistics usually ends up assuming a functional form for for this distribution D. Okay, so you assume something like a normal, you assume something like Bernoulli, you assume some kind of explicit distribution for these things. Okay, but in modern applications, like let's say you take machine learning, right? So in this case, your data consists of complex things like images or sound files or something like that. And as you can imagine, it's very unlikely that an image file will be distributed like a high dimensional Gaussian or something like that, because that would just be in extremely blurry images, right? So you assume often that there is some distribution D that has some reasonable properties, right? So that has some mean mu and variance, let's say less than or equal to 1, variance sigma squared, but it's less than or equal to 1, let's say. So let's say I normalize an image or something like that, and I have some property like this, and maybe I have other things as well. So there are these quantities called moments. So you assume that this distribution is nice in some way. Okay, so this is the more modern take on assumptions for distributions. So you don't assume an explicit structure like people normally do in statistics, but you assume that, oh, okay, I don't know this distribution. I can't tell you what its functional form is, but I know that it has some mean mu. It has some variance which is small enough, and it is nice in some other ways, like it's maybe smooth and so on. Okay, so this is a more modern view, uh, and that's also quite useful when we are thinking about data distributions. Okay, so now that we have these distributions, okay, so let's so the important thing here is that we have assumed that they have a certain form, and there is some mean and variance of this distribution. So these are quantities that we are interested in, but we don't know right now. Okay, and even in this Bernoulli, there is this parameter P that we don't know. Okay. Now, how do you find this distribution given the data? Right. So then that is the question of this of the next chunk of the lecture, and this is this question of estimation.